Hello, my name is 張り切りすぎて a fourth-year student at Sapporo Kaisei Secondary School. Today, I would like to present the result on my personal project on the Quantum Approximate Optimization Algorithm, or QAOA. Have you ever heard of QAOA? QAOA is an algorithm developed using quantum computing that can solve various combinational optimization problems we encounter in our daily lives. While it is expected to solve complex problems more quickly, there aren't many studies that have empirically demonstrated its effectiveness. Therefore, I decided to implement QAOA, solve problems with it, measure the time it takes, and compare it with classical algorithms to verify its effectiveness. My project is titled Testing a Quantum Approximate Optimization Algorithms to Solve Combinational Optimization Problems. In this video, I will explain quantum algorithms and QAOA and introduce the result of my experiments. My goal is to help you understand more about quantum computing and algorithms, which have been gaining attention in recent years. Here is the table of contents of this video. First, I will provide a brief definition of quantum algorithms, followed by an explanation of QAOA and the max-cut problems, which serve as the objective function in the studies. After formulating and solving the problem to make it easier to understand, I will present my research results. Let's begin by explaining what quantum algorithms are. Quantum algorithms are algorithms based on the principle and mathematics of quantum mechanics, executed on the computer known as a quantum computer. So how does quantum computing differ from conventional computing? In conventional computing, referred to as a classical computing in this video, calculations are performed by manipulating basic units called bits. As you may know, bits can exist in one of two states, 0 or 1, and various operations are performed using these two states. However, in quantum computing, calculations are performed using basic units called qubits. Unlike classical bits, qubits can represent an infinite number of states through a linear combination of basis vectors. Basis vectors are fundamental units in vector spaces, and a linear combination is a sum of these vectors. Qubits use a notation called bracket notation, where the states are represented with vertical verts and angle brackets. Let's take a closer look at the expression next to these qubits. The symbol of the left is called psi, representing the quantum state or wave function. On the right, we see Ket0 and Ket1, each manipulated by alpha and beta respectively, and they summed. These coefficients are called probability amplitude. Now, what advantages do qubits offer? The two main advantages are superposition and entanglement. Let's first talk about superposition. In quantum mechanics, the concept of measurement is crucial. Quantum mechanics deal with very small particles like electrons, whose states remain unknown until they observed. This may sound a bit strange, but if you're curious, I recommend looking up the Schrödinger's cat paradox. In quantum computing, superposition allows us to create a state that simultaneously holds multiple possible solutions, enabling efficient computations through repeated measurements. How can we manipulate these superposition states? As I mentioned earlier, a wave function can be expressed as a linear combination of basis vectors, with the coefficient called probability amplitude. Upon measuring the wave function, the states collapse instantly into one of basis vectors, with a probability determined by the square of the amplitude. For example, in the case shown here, applying the Adamar gate, which is a unitary matrix, to Ket0 creates a superposition state. In this wave function, the coefficient for each vectors are 1 over root 2, and when squared, they yield 1 over 2. This means that upon measuring this wave function, there is a 50% chance of collapsing into Ket0 and 50% chance of collapsing into Ket1. It may seem this odd, but I hope this helps you understand the concept better. Next, let's discuss entanglement. This is a phenomenon where two or more qubits become linked, so measuring at one qubit instantly affects the state of the another. For instance, let's example on the right represents the entanglement of two qubits. The Ket00 and Ket11 represent the tensor product of Ket0 and Ket0 and Ket1 and Ket1, respectively. When one qubit collapses either Ket0 or Ket1, the other qubit will immediately collapse to the same state. By utilizing principles like superposition and entanglement, quantum computing can manipulate quantum states to hold multiple solutions simultaneously, allowing for efficient computation. We will explore this concept further in this next slide. Now, let's take a look at the overview of QAOA. QAOA is a type of gravitational quantum algorithms designed to efficiently solve certain NP-hard combinational problems. But what is VQE? VQE, or the gravitational quantum eigensolver, is an algorithm based on the gravitational principle, which can solve eigenvalue and eigenvector problems for Hamiltonians. Eigenvalues and eigenvectors are properties of matrix where, when the vector is manipulated by matrix, the direction of the vector remains unchanged, but the magnitude is scaled by a scalar. The scalar is called the eigenvalue, and the vector is called eigenvector. For example, when applying a z-gate into Ket1, the result is minus Ket1, indicating that the vector is scaled by minus 1 along the y-axis of the Cartesian coordinate system. Therefore, one of the eigenvalue and eigenvectors of the matrix is minus 1 and Ket1. Similarly, applying a z-gate to Ket0 results in no change, so 1 and Ket0 are also eigenvalue-eigenvector pairs. How does VQE solve problems? It does so by setting the eigenvalue of Hamiltonian as a solution to the problem and finding the minimum eigenvalue of the Hamiltonian to solve the problem. The equation on the right represents a gravitational principle. It states that the expectation value of a Hamiltonian, sandwiches between a wave function parameterized by theta, is always greater than or equal to the ground state energy. VQE optimizes the parameters to minimize the expectation value using classical computer to iteratively approach the ground states. QAOA enhances VQE by incorporating quantum annealing, which involves evolving the Hamiltonian over the time to find desired eigenvalue. The capital T represents the total time, and the lowercase t represents a specific point in time. As time progresses, the system gradually converges to desired Hamiltonian. These methods are used to find the eigenvalue or solution to the problem. Here is a quantum circuit diagram. First, an Adama gate is applied to create a superposition states, followed by the application of matrix called the cost unitary and mixed unitary to perform the computation. The results are then measured, and the expectation value is used to optimize the parameters until the optimal solution obtained. Next, let's discuss the max-cut problem, which served as a cost function for this study. The max-cut problems involving dividing the node of the graph into two groups in such a way that the number of edges between nodes in different groups is maximized. For example, when nodes are divided into black and gray groups, the edges between nodes of different colors are cut. In this case, there are 8 such edges, so the result is 8. The max-cut problem can be formulated as follows. Instead of representing the group with colors, we use 0 and 1 to indicate the different groups. If adjacent nodes have the same color, the values xi and xj will both be 1 or 0, and when substituted into equation, the result is 0. However, if xi and xj have different values, the result is 1. The symbol on the right, called sigma, indicated that we sum this expression over all edges. Therefore, maximizing this expression means placing adjacent nodes in the different groups as much as possible. This can also be formulated as a minimum cut problem by reverting the sign. Now, why did I choose the max-cut problem as a cost function for this study? There are 3 main reasons. First, it allows us to approach real-world problems. For example, if you have a graph representing the friendships and want to group friends in such a way that a few of them are possible end up in the same group, this can be formulated as a max-cut problem. In the next slide, we will actually solve a grouping problem. The second reason is that the max-cut problem is well known as NP-hard problem, with extensive literature available. Optimization problems can be classified into 4 categories: P problems, NP-complete problems, and NP-hard problems. NP-hard problems are particularly challenging because their computational complexity increases exponentially, making it impossible for general-purpose computers to find exact solution. Since the max-cut problem is known as an NP-hard problem, if QAOA can solve it more quickly, it will demonstrate the effectiveness of QAOA. The third and most important reason is that the max-cut problem can be easily expressed in the QAOA format. QAOA, or quadratic unconstrained binary optimization, is a method for expressing the cost function using binary variables 0 and 1. When using quantum algorithms like QAOA, it is necessary to convert the problem into the QAOA format, or the Ising models, which uses binary variables 1 and -1. Now let's actually solve a problem. Let's solve the max-cut problem for this graph. Labeling the nodes from 0 to 4, we see that there are 6 edges connecting nodes 0 and 1, 0 and 3, 1 and 2, 2 and 3, 2 and 4, and 3 and 4, with 5 nodes in total. The max-cut problem for this graph can be formulated using sigma notation described earlier. Sigma ij of xi plus xj minus 2xi xj. To run QAOA, steps like inputting ansatz and specifying a mixer are required, but libraries like Qiskit or BlueCat can automate these steps. The matrix representation is known as a QAOA matrix, which can be generalized as shown on the right. By substituting xi equals si plus 1 over 2, it can be transformed into an Ising model with values of -1 and 1. In this experiment, I used the z-gate to represent the Ising model and calculating using QAOA. When running this code, it outputs the nodes 1 and 3 are in the same group. And upon verification, we find that the maximum cut of 7 edges is achieved. Now, let's introduce the research content. This time, I compared the performance of QAOA implemented with Qiskit against brute force search and classical solver called Groby. I conducted the experiments in the virtual environment using Visual Studio Code as a code editor. The versions used are listed on this slide. To measure the time, I used the time.time method. The diagram on the right showed the flowchart of the experiment. First, I created graph using RustWorks, then convert them into cost functions suitable for each solver. After starting the timer with time.time, I executed the functions. Once execution was complete, I recorded the end time with time.time and calculated the execution time by finding the difference from the start time. Then store the execution time in a list. Finally, I visualized the data using matplotlib. In this experiment, each function was run separately to ensure that the execution time of one function did not affect the others. Here are the results of the experiment. The graph on the left shows the execution time of brute force search, Groby, and QAOA with 1 and 2 steps. The middle graph compares brute force search, Groby, and QAOA with 1 step, and the graph on the right compares brute force search and Groby. The result indicated that QAOA generally took longer to execute, and classical solvers outperform QAOA in both execution time and accuracy. Let's take a closer look at each dataset. First, the comparison between brute force search, Groby, and QAOA with 1 and 2 steps. In this experiment, the number of nodes was varied from 4 to 14. For small-scale cost functions like this, classical solvers and brute force search outperform QAOA. Additionally, classical solvers achieve higher accuracy. Looking at the execution time of QAOA, it increased exponentially as the problem size grew, but in some cases, it solved problems faster depending on their shape and size. This can be attributed to the fact that QAOA is highly dependent on the problem's characteristics, and since QAOA was simulating on the classical computer rather than the quantum computer, algorithms like Robbie, which are optimized for classical computing, perform better. Next, the comparison between brute force search, Robbie, and QAOA with one step. Similarly, QAOA execution time increased exponentially, while Robbie and brute force search achieved shorter execution time and higher performance. In fact, QAOA's computational complexity depends on the number of repetition p and the total number m, not on the number of nodes n. However, in this simulation, the benefits of QAOA were not realized. Finally, the comparison between brute force search and Robbie. The graph showed that brute force search execution time increased exponentially. This is because in the maxcat problems, there are two choices for each node, leading to an exponential increase in computational complexity expressed as 2 powered by n. For small-scale variable problems like this, Robbie performed the best. In conclusion, the experimental results showed that the QAOA simulation could not outperform classical solvers. 3 reasons were identified for this. First, since QAOA was simulated on a classical computer, it couldn't leverage the advantages of solving NP-hard problems in a polynomial time, which QAOA is known for. Consequently, algorithms like Robbie optimized for classical computing perform better. Second, the problem size was not large enough, making it possible to find exact solution through brute force search. Also, I wanted to conduct experiment with larger problems, the challenges of learning QAOA on actual quantum computers, and limited resources prevent me from doing so. In the future, I hope to conduct experiments using actual quantum hardware. Finally, QAOA's execution time is highly dependent on the problem setting and structure. To make QAOA more practical in real-world applications, I believe there is a need to develop tools that simplify the formulation process and conduct experiments on the actual quantum hardware. Here are the references. Although quantum computing is still in its early stages, the development of both hardware and software in the future is expected to solve significant global problems. I hope this video has helped you gain a better understanding of quantum computing. Thank you for watching this long video until the end, and see you soon.